maybe during the lab. Okay.
Yes, sir. Yes, sir. That's it. Thank you, sir.
Yeah. So can you see my screen?
Yes, sir.
Okay. I guess we can get started. Folks will join slowly. Yeah, so this will be the first advanced topic that you will be attending as part of this winter school. Uh, so just a disclaimer that whatever we discussed in the morning about caste and caste hierarchy, and I kind of emphasize that they are useful. So in this session, we will kind of find out that all the things that we have discussed so far, they are kind of points of concern when we talk about security. So we'll follow the same protocol. It will be good if you can post your questions on the chat box, but we will take it, during our break points once in 15-20 minutes. Okay. This is mostly because of online setup and then internet bandwidth issues, right? And then yeah, but feel free to ask questions. More the better. Okay, so this is a summary of what this winter school has provided you so far. So now you are aware of out of order processors, branch predictor, caches, TLBs, prefetchers, right? And then a bit of interconnect if not in detail. And so if you look at from the computer architecture point of view, these are actually termed as microarchitecture. Why? Because they are not directly exposed to the programmer, but they are there inside our chips to make sure that our programs run faster, right? So all the lectures that you have so far, they only talk about improving latency, mitigating latency from the processor side, pipeline, cache, TLV, page table walker, whatever, right? So now we'll see why all these microarchitectures that or the microarchitectural techniques that have been proposed from last 3-4 decades, why they are creating a new headache for the security community. Okay. So before we jump into the security aspects of microarchitecture, this is a 101 definition of what exactly it means when someone says it's secure, right? So there's a standard definition which is called the CIA definition, which stands for confidentiality, integrity, and availability. So confidentiality, you can actually correlate with your processor or process or an application. And the way it is defined is as a process or as an application, you don't see what you are not supposed to see. Right? You can actually correlate with your virtual address. You can correlate with your virtual memory, all other concepts, right? So if you are not allowed to see something, or if you're not supposed to see something, so you should not be seeing it. Okay, so that's the confidentiality aspect of it. The next level, which is a bit more tricky, which is integrity. And here, one process or one application can actually go one step ahead and then start changing the content, or maybe writing, overwriting. But remember, even if the process is not supposed to see or read, okay? And the final property is kind of pretty intuitive. It's availability, where there is a malicious application which is just trying to play a game by some kind of denial of service attack scenario. You can easily correlate with a last level cache where, let's say, one core is just thrashing by writing a big by accessing a big array using a loop. Then all other cores will be getting misses in their private in their last level caches. So this is one form of availability aspect of security. So in this session, I will be mostly covering the confidentiality part. That's the key. and then maybe later integrity if time permits, right? But confidentiality will be the highlight of this session. Okay, so you must have seen commercials from Intel saying Intel Inside, right? But from last few years, there are various kinds of interesting memes that have come up, which actually put various attacks inside. So these are some of the famous attacks that appeared in last 4 or 5 years. They are kind of Spectre Meltdown and all. That's not the whole point here. The key message that I want to send here is uh, performance was the actually key aspect when we talk about microarchitecture, but now security is also another aspect that microarchitects have to look into. Tons of media articles you will find through various blogs, various technical news articles, right? And then it won't be surprising to say that every now and then there is a new attack or there is a new way of leaking information through microarchitecture. It's happening almost every month, if not weeks. So with that, let's understand how information can be leaked. Then we'll try to connect information leakage with one of the simple microarchitecture cache. And then we will see what are the possible ways to attack a cache and leak information. Okay. So this is a code snippet or a pseudocode of a famous crypto algorithm. The crypto part is not important. We are actually discussing the architectural aspects here. So the key here is the variable e, which is also known as the exponent. And whoever the attacker is, it may be a process, it may be anything running in your system. It's trying to retrieve the value of e. So for the sake of simplicity, let's assume E is an actually array, and the length of the array may be of 64-bit, 128-bit, or whatever, right? And one of the victim application is actually using this particular crypto code. And if you can look at this code carefully, there is a for loop that is iterating based on the size of the exponent E. And there are a few operations that are happening based on the content of each index inside E. Okay. So if a particular index has value 1, then there is a multiply operation and followed by reduce. So reduce is nothing but the modulo. But if a particular index is 0, then we are not performing this multiply and reduce operation, right? So now you can easily correlate with the control flow dependency and control flow things that Govind must have talked about yesterday. And you can easily correlate that. So whenever I'm accessing only the square and reduce, that means that particular exponent bit is 0. If I am doing both square reduce and multiply reduce, then that bit is 1. Remember, these are addresses which will be mapped to memory. They will be there in the cache, right? So it will be easy to find it out whether they are actually on cache or not. We'll discuss that in a few slides. Okay. So with that background, let's see how we can extract or how we can correlate this with exact key through cache. Okay. So if you remember the morning session, I started with the notion of memory wall and latency as the bottleneck, and that's why caches come into picture. But now this slide will tell you that that is the main or the primary culprit for all these security issues. Okay, so this plot is showing access time. Remember the average memory access time for a particular load or a particular memory access. And you can easily see there is it's a bimodal distribution, right? So there are some latency numbers which are, let's say, less than 110 or so. And there are many latency numbers which are more than 250 or so, right? So easily you can deduce that the accesses which are taking less than 100 cycles, maybe they are coming from the cache. and which are taking more than 250 cycles, they are certainly coming from off-chip DRAM, right? So this is pretty easy to deduce, right? Once you have done that, then you need a mechanism to correlate this kind of access patterns that you are observing with the exact code that we have discussed here, right? The square reduce or square reduce followed by multiply reduce. So if you just look at the latency numbers and any latency numbers which are below 100, so you can say that, okay, these are the information which are there in the cache. I will see what are they. So usually you can correlate, okay, this is a 0, this is a 0, and this is SR followed by MR, so it's actually 1, right? So based on that, you will be able to retrieve the key, okay? But we haven't discussed how, like what exactly the attacker should do. So we are just going one step at a time. Okay? So what attacker can do, this is a pretty toy attacker, textbook kind of attacker, where we are assuming the attacker and victim, they are actually sharing a particular library. Let's say the crypto library is shared by both attacker and victim. And the code snippet that I showed, that can be easily converted into something like this. If there is a secret bit 1, then the victim accesses some address, otherwise it doesn't, right? So what the attacker will do, the attacker will use an instruction called CL flush. And the meaning of CL flush is you flush the content of a cache line from the entire cache hierarchy. Okay. So the attacker has flushed the address. Once it has flushed, it starts a timer. You can just use functions like get time of the day and accesses that address again. Remember, attacker has flushed it. That means the address is not there in the processor or its cache hierarchy, right? After accessing it, if it finds that the response time or the average memory access time is fast, which means victim has accessed it, right? So this is a pretty simple way to correlate that I'll be able to know whether victim has accessed address A or not. With the assumption that address A is shared by both attacker and victim, it is pretty common to share some of the libraries which are mapped to the address space of both the processes. Okay. So with that background, I will try to characterize the timing channels that we have seen, which actually exploits the timing difference between cache and DRAM into two broad categories of attacks, which are called the side channel and covert channel attack. So in the side channel attack, the previous slide that I have shown, so there is a victim which is running, let's say, a pretty security critical application, and the spy is not supposed to see. Even the OS is not allowing it to see, and as per the address space protection and everything is intact. But because they are sharing the cache, the spy is able to infer what exactly the victim is accessing based on the timing difference. Okay, that's why it's called side channel. It's actually not a legitimate channel through which the spy and victims should communicate, but because of our microarchitecture, it's providing a bypass route to get the data or to observe the data. The other extreme is called the covert channel attack, where there are no attacker and victim, but there are multiple attackers who are trying to play a game in the system. You can simply correlate this with, let's say, two spy or Trojans which are running in your system. And even if they are not supposed to communicate, so let's say as per the OS abstraction, that they are running different processes, they are not sharing anything, but through cache, they can actually communicate, okay, based on latency difference. So this guy can say that whenever you get a latency which is fast, that means I want to communicate 1. And whenever you get a latency which is slow, that means I want to communicate 0. So based on that, you can actually communicate information. Okay, this is at a high level abstract view. So we'll start jumping into the details slowly, one step at a time, and we'll mostly focus on the last level cache attack because that is shared by multiple cores in a multi-core system. And as I have already mentioned, the key here is there is a latency difference that is easily distinguishable when the data is coming from the last level cache or it's coming from the DRAM. So there are two categories of attacks. We already talked about this flush based attack at a high level. There are also eviction-based attacks. So if you remember my morning lecture on cache replacement policy, for a given set, whenever we get a miss, we start replacing or evicting that block, right? So eviction-based attacks are more practical. It doesn't demand any notion of sharing between attacker and victim. Sharing meaning sharing of OS pages. And what the attacker can simply do is it can start accessing large arrays which can kick out the blocks of victim. We will see how. So the keyword is eviction here. And then in the previous case, the keyword was flush. Okay. The threat model for this session, we'll try to make it pretty simple. We'll say that the attacker is successful if the attacker comes to know that a particular cache set has been accessed by a victim. Okay, forget about exact address. As long as we can say that, okay, set number 100 was accessed by victim, we will define that as a successful attack, at least for this session. Okay. Any questions so far before we jump into more details? So I'm looking at the chat box. If there anything you can type or you can unmute. Okay, so I'm assuming all good. Okay, so then let's move on. So now let's look into all these attacks in a more detailed way. So the first attack that I was talking about, or first of its kind, is the flush reload attack, where the attacker uses a specialized instruction called CL flush, right? And the assumption is both attacker and victim are actually using a shared library or any shared memory, and that's why both of them can actually access a particular address, right? And but remember, the goal is to find out whether the victim has access or not. Okay, so this is the process. The spy actually it maps the shared library. So that means it will be mapped into its own address space. So obviously it will be there in the cache. Then the spy flushes. The victim reloads whenever it needs it, right? So reload meaning loading it from the DRAM. And finally, if the spy reloads or tries to access the same address again, if it gets a hit, it is certainly the case that victim has accessed that block, right? Because the spy has already flushed it out, right? So this is the simple attack that you can mount it on your laptops or desktop. Okay. There is a variation of this flush-based attack, which is called Fluorescent Plus, where everything remains the same. First the attacker flushes and the victim reloads, but finally the spy flushes again. Okay, instead of trying to access the address again, it flushes that address again. That means it uses a CL flush in step 1. It also uses a CL flush in step 3, and observe the timing difference. But in this case, the subtle issue here is if you get a hit in the cache, that means it will take more time, which is kind of counterintuitive to what we have discussed so far. Okay, so just pay attention here. If you are getting a hit for a CL flush, you have to do more operation because there is something valid present in the cache. You have to flush it to the DRAM. If the data is not present, it will take less amount of time. Okay. So these are some of the latency numbers from some of the Intel machines. If you look at, you can take any, let's say the first one, EV Bridge, you can see that on a hit, the latency is, let's say, somewhere around 105 or so. But in case of miss, it starts from 110, goes till 130. So the range is different. For a hit, the range is 100 to 125. For miss, it starts from 110 to 130. But the key is you have to look at the probability distribution, right? What fraction of time these things happen. Having said that, these attacks are extremely noisy because you can see the gap is just few cycles, 5 or 10 cycles. So in real system with multiple processes running, this attack is not that effective. And then you may not be able to deduce or differentiate whether the victim has accessed it. Okay. So now we'll move on to the attacks where there is no assumption about page sharing between attacker and victim, and can we still get information about the victim. And one of the popular attacks or the popular eviction based attacks is actually known as the prime and probe, where what attacker does is, this is again at a abstract view, the spy fills the entire cache. Okay, so you can easily do it by writing a for loop and trying to access an array which is larger than the size of the LLC. And then remember, this is a fixed size resource, and when the victim comes to access its data, it will get missed because the spy has already filled the LLC with its own data, right? Now the spy probes again, meaning spy tries to access the same addresses again, and now the spy will get misses, meaning it will observe longer latency because victim has come in between and it has evicted few blocks of the attacker or the spy, right? So if the attacker gets longer latency during the probe, which means this is the set of interest, right? That means this set was actually accessed by victim. And then as per my threat model, I said that if I can say that, okay, this is the set that was accessed by the victim, then I'm a successful attacker. Okay. There are various parameters of interest while mounting an attack because we have no control about victims execution. Okay, so although we talked about the notion of priming it and then waiting for a few time and then probing it, but it may happen that during the entire process victim never comes or victim never accesses the LLC. Ideally, you would like to have the victim accesses during the wait step of the attacker because the attacker has already thrashed the cache. It is waiting for the victim to come, and then finally it will observe or probe, right? But you can have various combinations. The attacker can come the victim can access multiple times, or the victim may come during the the interphase interval during the wait and probe phase. So then in all these cases, your observation will be noisy. Typically, for the applications that have been attacked so far, a gap of 5,000 to 10,000 cycle is good enough to have a clear distinction between whether the victim has accessed or not. But it's not a rule that you have to follow. Depending on the application, this number may vary. Okay. Another thing that I want to emphasize here is the notion of different cache hierarchies that we discussed in the morning. One of them was the inclusive cache hierarchy, if you remember. So just a quick recap. In the inclusive cache, we said that the last level cache is a superset of private caches. That means whatever data is there in the attacker's private cache, it's also there in LLC. Whatever data which is present in the victim's private cache, it's also there in LLC, right? Now, when the attacker does prime probe attack by thrashing the last level cache, because of fixed capacity or because it's mapped to the same set, the block of victim will be evicted. And now once the block will be evicted because of a replacement policy, just to maintain the inclusivity property, now the cache controller at the last level cache will send a request to all the private caches saying, if you have this address, please invalidate yourself or please kick out itself, right? So this is actually helping the attacker. If you look at an inclusive cache, the attacker can control the contents of a private cache of a victim by just thrashing the last level cache. But this is not possible in non-inclusive caches and exclusive caches. Although probabilistically it's possible, but it's not that simple. Okay. So you can easily correlate whatever ideas that we discussed in the morning. They are actually now becoming points of concern, right? The simple ideas which are helpful, that they are creating more and more security issues. Right. So I'll pause again for any questions because this is an advanced topic. I don't want to just jump into many things without any understanding.
Sir, hello.
Yeah, please go on. Yeah.
Sir, because this topic is new to me, so I have a small doubt.
Mhm.
Uh, so is hardware attack is related to only to data servers where there is memory or whatever you are talking about cases, or it can happen in personal computers?
No, these are not hardware attacks. Just to make it precise, these are
Uh,
micro-architecture attacks. Okay, so hardware attacks are a bit different, where the attacker has the access to, let's say, the internal DRAM. It can touch the DRAM. It can actually observe the power difference, temperature difference, or blah blah blah. Right?
okay, okay.
Okay, but yeah, so this microarchitectural attacks can happen anywhere, right? So it can happen in a, in your institute's lab, right?
Mm-hmm.
Where you are sharing your machine with some of your friends, even
Okay.
though they have their own username and password, but they can actually probe the cache. Cache is shared to both of you, right? You and
Yeah,
your
yes.
friend, right?
Uh,
So if your friend wants to know, okay, whether you are using an AES library, then the friend can mount a private probe attack in your remote machine,
okay.
right? Yeah.
Okay. Okay, sir.
So from the user perspective, will there be any change in kind of access time or something, which can kind of indicate whether there is an attack which is actually actively going on?
Yeah, so this is a good question. So what you are suggesting is, can we have a detector, right? Which can, or can we have some indication that the attack is actually
Yes,
happening at
sir.
the moment, right? So this is an open problem. Although there are proposals in the research community, but this is an open problem. It's a difficult problem to detect, because it's kind of a cat and mouse game. Every time you kind of detect that, okay, these are the best ways to detect an attacker, the attacker may come up with a new fancy way of attack, right? So every time
Yes,
you have
sir.
to
Something
chase
to
the
fool them.
attacker, right? So yeah.
Yes, sir.
Okay, more questions?
I think someone has asked one in the chat.
Oh, is it? Oh, okay, yeah, Nikunj. Okay. Since attacker uses last level cache to attack, does it mean that microarchitecture security can never be optimized by increasing the number of cache level or any other cache parameter that may provide optimum security? Wow, this is a heavily loaded question. Uh, See, the answer is yes and no. It depends what additional parameters you are bringing in to the table, which is already not there, right? So even if you add another level, it will have the similar parameters. There will be the sets, there will be indexing, there will be some comparison, there will be latency difference, there will be replacement policy, right? So whatever you are asking, these are all open problems. So if you are actually doing an MS or PhD, so these are the problems that you should look for, that how exactly you should design your cache so that all these attacks won't be possible. What should you do to your replacement policy? What should you do for your indexing? We will discuss some of them maybe in the last part of the talk, but these are all open problems. Okay, does that answer your question, Nikunj? Maybe just a thumbs up will do.
So is it
Maybe.
possible to use like a separate cryptographic hash for each of the process so that you can never know what is the actual kind of memory it is trying to access or whatever?
Yeah. I will discuss that in the last part of the talk. We'll discuss some of the things. Okay.
Okay, sir.
Uh, okay, there's a question from Prithvi. In the flush and flush attack, how is the attacker benefited since no data manipulation or usage by the attacker? Yeah, so let's look at the flush and flush. Okay. See, here the goal of the attacker is to understand, let's say the example that I gave, right? To find out the value of E, right? And the attacker knows the address to which that particular E is mapped, right? Let's say that is part of the library, that is the address space. So the attacker knows these are the addresses which are shared by me and victim. Now, what attacker does, instead of writing a load instruction or just accessing those libraries, it uses the instruction CL+. So it's like within a for loop, you CL+ address, wait for some time, then again CL+, CL+, wait, CL+, continuously, right? And the comment that I made here is, In the step 3, if the attacker is taking more time to flush it, that means between step 1 and step 3, someone has actually brought the block into the cache, right? And depending on the access pattern, depending on just a minute. Yeah, depending on the latency difference and depending on what you want to extract, you can easily get this kind of access pattern and do a post-mortem analysis. Okay, so is that clear, Prithvi? Okay, so there is one more Pratyush or Jackhammer and Rowhammer. I don't know about Jackhammer, but I certainly know about Rowhammer. Whether Rowhammer attacks considered in confidentiality domain? No, no, no. So Rowhammer is an attack which is violating the integrity. So let me just spell it out what exactly Rowhammer attack is. This is actually at the DRAM level. Since we haven't talked about DRAM so far, I didn't explain that. So the idea of Rowhammer is you kind of try to access one DRAM page or one DRAM row again and again continuously within a loop, which is indirectly termed as hammering a particular row in DRAM. And the side effect of that is the adjacent rows or the adjacent pages in DRAM, they get affected. So the simple example will be suddenly the ones will become zeros, right? So that means you are affecting the integrity. Something that you are not supposed to see, you are overwriting it, right? It's one step ahead of what we are discussing now. Is that clear, Pratyush? Okay. Okay then, so let's move on. So the obvious question now comes is how practical these attacks are. So, are there attacks that are done on real system in a real world where, let's say bank transactions have been hacked into or something like that? Well, the answer is no. These are still, I would say, compared to the software attacks or the other systems attacks that you may be aware of, they are kind of in the infant stage. It may happen that in future we may get more and more, vulnerability and more attacks which are kind of practical. But I will actually answer this question after a few slides, and I will stress that even if they are not that practical at the moment, why we should be bothered about it and why we should try to fix it. Okay. So to answer that question, I will actually jump into two attacks called Spectre and Meltdown. So these two attacks, they use cache as a timing channel to extract information. Although they use cache as a timing channel or a side channel, the key idea of these attacks is they exploit the aggressive processor design in the form of speculative execution and out of order processor. So I'm pretty sure Govind and Arka would have talked about out of order processor and speculative execution in yesterday's lecture. So let's see this particular attack, what exactly it is. Okay, it's a bit subtle. If you don't get it, pause me just after the Spectre attack, we can revisit. Just a 4-line code, and this code is actually part of it can be part of any library, it can be part of any process, anything. Okay, let's not get into the technicalities, or let's not bring complexity here. The key here is the attacker is trying to access an array, which is the cause array, and that is not mapped to attacker's address space. Okay, that means from the OS perspective, attacker is not allowed to access this particular array. The attacker is not supposed to see what is there inside this array, right? However, for some functionality, the attacker is providing a parameter for victim to execute some of its function. Okay, and in this case, the parameter is the variable attacker. Okay, and it is initialized to 4 pretty intelligently. We'll see why it's an intelligent move. And then this is the $1 million effect. Okay, So this if condition checks whether the value of attacker, which is 4, is less than the size of this cause array, right? And the size of the array is actually 3. That means this particular statement is actually false. So the program should not access all these arrays or any statement after the if statement, right? However, uh, and then there are other assumptions that the attacker has already flushed out, the caches or thrashed out the caches. That's why this particular array, which is actually accessed by the victim, is not there in the cache. So for anything that is that is coming from this particular array, it has to go to DRAM because the attacker has already thrust it. Okay. Now let's see why branch predictor and speculative execution are kind of helping the attacker. So we are actually stuck with this particular if statement, and we say that the statement should be false, but to our surprise, the branch predictor actually returned true. Now the question is why? It's pretty obvious and intuitive. The branch predictor should have said, no, this condition is false, right? The branch predictor says true because the attacker has actually mistrained the branch predictor. How? By sending request or by already using code where the value of attacker is always less than 3, right? So because of that, the branch predictor has trained itself in the form of true all the time. So you can simply correlate it with the 2-bit predictor if Govind has talked about it, right? And now the attacker has actually mistrained or fooled the branch predictor, and the processor has actually started executing this part of the program. Okay, even though it's not supposed to. And now what will happen? The processor is in the wrong path, which is also known as the speculative path or the transient path. Okay, the processor is assuming that the branch predictor is right, but eventually the processor will realize that it's actually not. But as I have mentioned, this particular array is actually not there in the cache. So accessing anything related to this array will actually go to DRAM. That will be around, let's say, 100 to 200 cycles. And in the meantime, the processor has already retrieved the corresponding data, right? So there is some index here, cause array index 4, right? And it has brought it into the caches. So now the situation is the data is actually present in the private caches or even the last level cache. So now what you should do, you guessed it right, you can just run a flush reload or prime or probe cache attacks to get the exact value. So this was actually the secret. Okay, we are not supposed to touch it, but we will be able to get the exact value. Let's see how. So eventually the processor will realize that it's a mistake. So it has to undo or flush out all the wrong path instruction. But remember the cache has the data because the processor has moved ahead and it has brought the data. Now what the attacker will do, attacker will try to access its own array, okay, which is my array. That attacker is able to access because that is mapped to its own address space. And it will just run a loop like my array 0, my array 512, my array 1024, and observe the access time. Suddenly for 1024, it's seeing that it is able to access the data pretty fast, with just 5 nanoseconds. That means the data is actually coming from the cache, which means the value of this particular index was actually 2. That's why when attacker tries to access 2 into 5121024, it got the data in just 5 nanoseconds instead of 60 nanoseconds, right? So now you can see that you are able to get the data, not only observe what was the access pattern, now you are able to get the data that was not mapped to your address space. Just one slide before we may pause. The other attack is meltdown attack, which is pretty intuitive and it has nothing to do with the speculative execution, but it is actually a curse from the out of order execution. So let's look at this 3-line code with one comment. The first line is an exception. Okay, that means you will actually call an exception handler, right? And you should not start executing anything after step 1. But if you look at statement 1 and 3, they are independent. So our modern processor, what it will think is it's better to reorder them just to improve instruction level parallelism and to improve IPC, right? But this is actually a kernel array. From user level, you are not supposed to access it. And then definitely it should raise a page fault or a protection fault, right? But as I have said, we don't handle, or the processor doesn't handle the page fault or any wrong prediction immediately. It does it when it reaches the head of the ROB, when it actually tries to commit the instruction in order, right? And that gives sufficient time for the attacker to load the entire array into cache, and then you can do whatever we discussed in the previous slide, right? The attacker can just write a for loop and try to access all these things. So in reality, you can actually dump the entire OS image into your cache and access it from user space, right? So this is, if you just think about it, this is really scary. I will pause here and take questions before we move on. Is Spectre Meltdown clear?
Yes, sir.
Yeah, feel free to let me know if you have anything that is not clear, because it's a bit subtle. It's not that straightforward. If not, then it's good. So that means you have the basics of computer architecture, so you are able to connect all the dots now.
So is there a reason why we are using some large numbers like 512, 4096?
Yeah. So there are various regions. So they are actually, they are used with the notion that they actually go to a different page. They are not part of the same OS page. So if you look
Okay,
at,
sir.
the page size is 4 KB typically, right? Unless you go for a, huge page of MBs and GBs, right?
Yes, sir.
And you can also put a different number based on the cache size or associativity, right? So this is just a number based on the attacker's code, or the authors who proposed it on their machine, right? But you can also come up with different values here depending on page size, cache size, and other parameters.
Okay, sir. And this will be OS agnostic, like it doesn't depend on the operating system.
Yeah. Yes. It's always agnostic. It was successfully mounted on Mac, Windows, Linux. Yes, all those.
Okay, sir.
If there are no more questions, so then we can move on. So now that we have talked about the offensive side, which is the attacks, it's also important to discuss what are the possible mitigation techniques that we can propose to mitigate all these attacks. Okay, so these are the slides that I brought it from my PhD student Yasika, who is the TA for today's afternoon lab. So broadly, the mitigations are actually can be categorized into two techniques called cache randomization and cache partitioning. So we will go through them one by one. So before jumping into mitigation, let's look at what all we have so far. So if you correlate with the morning lecture on caches, you will find that there is a one-on-one mapping between address and index bit, right? And then we said LLC is shared among multiple cores in a multi-core system. And third is there is a latency difference that can be easily distinguishable whether you are getting the data from LLC or from DRAM. Now, if you have to provide security, then you have to break all this basic definition that we have discussed in the morning, right? Let's start with the first one, which is the mapping itself. Can we come up with a non-deterministic mapping? So when we start with the notion of non-determinism, then the first thing that comes to our mind is, can we kind of randomize these index bits? Can we come up with new hash functions which can always try to change the index bits automatically, and then because of which the attacker won't be able to know whether this particular address is mapped to this set or that set, and it won't be able to mount a eviction based attack, right? So just to illustrate, so for example, now address A0 and A1 are mapped to set 2, but through randomization, they can actually map to any set, right? But the key here is you should actually use encryption engine, and that can provide you a key so that you can randomize and re-randomize regularly. If you just randomize once, then again it becomes deterministic, right? So the idea should be put an encryption engine beside your last level cache, generate a key, use that key to generate the index or the set number. Once you have done that, maybe depending on how agile your attacker is, you kind of remap or rekey the same index bits again and again in a regular interval. Okay, so that's the idea. You have to periodically change the key or periodically change the indexing so that attacker won't be able to guess what exactly is happening. Okay. I won't get into the details because these are advanced topics, but a high level idea is have an encryption engine that can provide you a key, use that key to get a set number, and don't forget to remap it. Okay. So one of the limitation of this kind of mitigation technique is, see, we are just breaking the determinism between the address and indexing, right? But the cache is still shared among multiple applications or attacker and victim. So yeah, it may be the case that with randomized caches, the life of the attacker is becoming difficult, but certainly there is a non-zero probability that the attacker can still mount the attack. Okay, maybe it will be highly probabilistic. So it all depends on how fast your attacker is, how quickly it can attack and other things. Because based on that, you have to remap or rekey your blocks frequently, right? Possible mitigation technique is called cache partitioning, pretty intuitive. Uh, if you remember, we said that LLC is shared among multiple applications. So what if we break that statement? We say no, it's no longer shared, and then it's not private although. Okay, so don't get confused. It is actually the last level cache which is shared by multiple cores, but dynamically we can create isolated regions. Let's say for each process, I will provide few KBs or few MBs that particular process will be able to access, not all, right? So there are various ways to implement or come up with this functionality of cache partitioning. The first one is page coloring. A pretty neat idea. Let's look at how it can be done. So the page coloring algorithm actually tries to change the indexing function, and based on that, it will make sure that each core has its own set of addresses or own set of blocks which are completely isolated. Okay, let's see how it can be done. So these are the typical address mapping techniques that we have talked in the morning. You have tag bits, you have index bits. So in this case, we are talking about a cache with 2048 sets and a block size of 64 bytes. Now, if your page size is 4 KB, the OS page size is 4 KB, then that means the lower LSB 12 bits are kind of gone for block offset and part of LLC index. But you still have 5 bits left, which are contributing to the indexing, right? Now, what you can do is you can use this 5 bits to make sure that all your indexing are actually mapped to 2 to the power 5 different regions. Okay, that's why they are called coloring, because it creates 32 different colors. And in this case, each region is of size of 64 KB, depending on the numbers that we have discussed so far. Okay, so this is how it will look like, right? You have your physical memory, and now you have different regions at the last level cache also. And remember, each color corresponds to each process, right? So that means no two processes can access the same set. They are isolated at the indexing level. Okay. You can go through this particular slide maybe in a more detail to understand other subtleties, but in the interest of time, I'll just jump into the limitation part of page coloring. So one of the primary limitation of this technique is this is based on the OS approach, right? So the OS allocates memory. Based on that allocation, you are allocating LLC. This is good as long as your memory requirement and cache requirements are kind of similar. That means if your DRAM requirement is high and cache requirement is high, and there is a direct correlation between them, then that's a good technique. If it is not, then it may happen that you need small amount of LLC but more memory, or more amount of LLC or small memory, then you will be eventually wasting your memory space or cache space, which can lead to performance degradation. The other approach to implement cache partitioning is way partitioning. Remember, we talked about two-way, four-way assertive cache. What if we kind of divide our ways to multiple applications, right? So now the spy, if we are dealing with a four-way assertive cache, the spy will have, let's say, two ways. The victim will have two ways. And remember, even the cache replacement policy will be limited to their own ways. Okay, so the spy can't replace or evict something from the victim's ways. Okay, so this kind of things are already implemented in commercial machine. For example, Intel Cat is one of the ideas that you can go and refer and see that this kind of partitioning is already there, right? Again, I won't go into much more details about these topics, but one of the limitation of this particular partitioning is the number of isolation boundaries that you can create is limited by the number of ways. If you have a 16-way assertive cache, that means at max you can create 16 isolated regions, right? And not more than that. But what if your system is running 32 processes, right? Then there is no clear answer how to handle it. Finally, it's a set partitioning similar to page coloring, but instead of using page coloring, use another mapping function which can decide on the fly what is the requirement of an application, how much memory it wants, and then you can actually create a notion of clusters. Remember, we started with the notion of byte, then line, then set. Now I am bringing another term called cluster, where each cluster is collection of sets, right? And they are completely mutually exclusive. So one application won't be able to see or access the cluster that is not mapped to its own address space, right? And that can be done through various ways. One of the ways is actually you can have a mapping function which makes sure that these are the sets that are mapped to application one. These are the sets which are mapped to application two. Okay, it can be non-contiguous. It can be it may not be power up to. You can try whatever you want. The only downside of this is who will decide how many clusters you want. Who will decide what is the requirement, right? So basically, you need some information or some support from the top of the system stack, either OS or maybe programmer or runtime, right? So these are the issues with this approach. We also talked about the Spectre Meltdown attack, which has a different way of attacking the same cache, and just isolating may not help. So for that, what you need to do is you can actually come up with a better cache hierarchy, where you will say that, okay, whenever my processor is actually operating in a speculative mode, right, in the wrong path, that time I will actually put my data in a specialized cache called, let's say, L0 cache. These are tiny caches which are used only for storing data when the processor is executing in the speculative mode. Okay. And what you can then do is, for once the instructions are committed, that means they are no longer in the wrong path, then you can put them back into the rest of the hierarchy, L1, L2, L3, and blah, blah, blah. In this way, the Spectre attacker won't be able to use cache hierarchy as a side channel to mount Spectre attack, right? So the basic idea is you bypass the DRAM response during the speculative part, put it in a speculative cache. Once it is committed, once you know that the instructions are no longer speculative, they are actually on the right path, you put it back into your actual caches. Okay. So obviously there are other subtleties that I'm not going through it. I'm just giving you a high-level overview. Another important aspect of all these ideas is, on a context switch, you have to make sure that you kind of invalidate all the entries in the cache. Otherwise, a new process may come and start accessing this data through different flush reload or prime and probe attack, right? I'll pause here. We are kind of entering into the last part of the talk. Any questions on the mitigations?
The Spectre attack, if the compiler itself knows that at compile time that this loop is false, it can remove it, right?
Compiler can do many things, but not everything, right? Because compiler has no idea about the dynamics of out of order processor, like how many entries are there in the ROB, how many stages of pipeline the processor is using, right? And at the runtime, you may have a completely different picture altogether. Having said that, there are proposals from the compiler field where when you generate the code, you make sure that this kind of gadgets or code gadgets are not generated by the compiler. Does that answer your question?
Yes, sir. But as such, compiler does optimization, right? That
Yes,
if
yes. That's what I'm saying.
less than
Compiler can do, but how effective it will be in all the cases, that is a bit debatable. Okay. Yeah. Compiler can certainly help.
Sir, what does it mean if processor is in working in speculative mode? So what does it mean?
Yeah, so I'm not sure whether you have attended Govind's lecture yesterday. So speculative mode meaning, let's say there is a heap condition, and then the branch predictor is actually it's not that highly accurate, but it actually say that okay, that particular heap condition will be taken, so the processor should move on, right? So the processor actually moved on and started executing all the instructions that are inside the heap condition. Okay, assuming it will be true, right? Eventually, when the instruction enters the final stage of the pipeline, when all the checkings happen, that whether the instruction is actually correct instruction that the processor should have executed, then the processor realized, no, the branch predictor made a mistake and I should not have executed it. So this is the speculative path. Is
Okay, sir.
that clear?
Yeah, understood.
Okay, thanks. Okay, Nikunj has a question. Can the OS image replicated by attacker for, say, any end processor be used to initiate attack on N+2, N+4, or further different processor which might have enhanced security? If yes, will that image can be further used to leverage all kinds of... Okay, I'm kind of confused because it's again bit loaded. Are you saying if the OS data structures are mapped to different processes, that's why it is kind of easy to mount the attack? If yes, then yeah, that's kind of true. So that was the basis for meltdown attack. So one of the mitigation techniques that folks from Linux they came up with to mitigate meltdown is actually to stop this kind of definition, right? So the address space won't be shared among all the processes, right? So the kernel will have its own page table, user will have its own page table, kind of, right? So there is an isolation from the OS point of view. Is that, Nikunj, what you wanted to ask, and is that the answer? Okay.
Sir, the new AMD chips, they use a chiplet kind of design because of which the cache hierarchy is somewhat different and the cache arrangement is somewhat different. So will this change the way these attacks are implemented?
Yeah. So I don't know whether others know about chiplet architecture. So let me just give a high level definition. So chiplet architecture is a new concept, if not completely new, but relatively new, where different providers, different vendors, they design their own let's say microarchitectural ideas or own memory and device and all. And finally, they are integrated through a technology called 2.5D integration. Okay, so the question that we got is, even in chiplet architecture, can we mount cache attack? You can, but the semantics will be a bit different. Okay, so you won't be surprised if you see attacks on chiplet architecture maybe in a year or two. There are already few attacks that are coming. Okay, but certainly it's possible, but it's not that straightforward. You have to find out something else, right? On top of what we are discussing now.
Okay, sir.
More questions on mitigations? Okay, Nikunj again. Can the fabrication of the chips be actually useful in optimizing and avoiding this microarchitecture? Okay, so that's a different ball game altogether. Here we are talking about microarchitecture and the design of microarchitecture, right? What you are suggesting is some kind of root of trust. When you fabricate a chip, you kind of provide a key or provide a signature or make sure that these attacks won't happen. That's a bit costly and bit difficult to achieve, at least in the current world, right? People are trying it. It's not like that this idea doesn't make sense. It makes sense, but there are many trade-offs that you have to look into. Okay.
So I had one question regarding the the mitigation technique where we were using a cryptographic key. That doesn't it just change the attack surface? So once you predict how the key is being generated, you can essentially replicate it on, say, your device and find out what will be the next arrangement of the cache or something.
Yeah. So your statement is correct, assuming the cipher or the encryption unit that you are using to generate key is not powerful. Let's say if I'll give you an extreme example, if you go for, let's say, AES, then you won't be able to do that. Okay. But
Okay,
there are actually papers that they talk about where they say that, okay, if you use pretty simple low latency block ciphers, the attacker will be able to deduce what exactly is the key. Then the entire attack surface is open.
okay, sir.
Okay. More questions? Okay, if not, we can move on. I think I'm almost done. So the summary of what we have discussed so far is that yeah, these are the attacks that are there and they will be there, right? But as we also emphasized, or we also debated, that they are not that practical, compared to other kinds of attacks that are already there in the system stack. Having said that, we have seen that if we would have solved the cache attack problem, then Spectre Meltdown would not have come, right? So it's just a connection of dots, right? If you connect all the dots, you will find that if you are not solving the problem now, tomorrow a new big problem may come which can, exploit the existing problem, right? So that's why it's kind of important to come up with more and more attacks and try to find out more and more vulnerabilities in the offensive side of research. And in the defensive side, the entire community now has to go down to the first order principle, right? How can we design whatever we have designed in last 40 years in a way which will make everything secure, right? And this is a hard problem because the moment you want to make anything secure, there is a price for it, and usually the price is in the form of performance or energy, right? So if you can come up with an idea which doesn't hamper performance, which doesn't hamper energy consumption, and still provide security, then it's the best solution for this problem. Okay. So the research question that I just talked about, right? But you can also look into some of the top forums, which are security forums, not related to microarchitecture security only, along with some of the computer architecture conferences that I mentioned during the morning session, right? Most of the research is actually about coming up with new attack, new threat model, or performance security trade-off, or the game that I have been saying, right? The cat and mouse game. You come up with a mitigation, I will come up with a new attack on that mitigation, right? And it goes on, right? So if you love this kind of game, then this is actually a field of interest, right? At least you can go and look at the papers or the ideas that are coming in, right? So with that, I will stop, and then I'll stop by wishing you all a happy 2022. and hopefully we'll be able to CL plus COVID-19. Right. Okay, with that, thank you. I'll be happy to take questions. We have around 7-8 minutes. Are there any questions that we can take? Okay, maybe it's lunchtime and all are hungry, but yeah, feel free to go through the video. I'll also upload the slides. If you are not clear about anything, feel free to directly text me, DM me. Okay, so we'll meet again at 2:30 for the labs. But if you haven't set up your infrastructure for the lab, then I would suggest you join us maybe a bit early, maybe 2:15 or so that we'll try to resolve all the issues and start the lab at 2:30 sharp. Okay.
Biswa, you will be available at 4 for the doubt clearing.
Yes. I'll be there. Yeah.
Thanks.
So for the lab, we don't need to use the virtual machine, right? We can just do it on our local system.
Yeah. You don't need a virtual machine.
Okay, sir.
Yeah. So whatever instructions that are provided by Yasika and Devasis, right? Just go through it. Try to do whatever is possible. If you are still struggling, we'll try to resolve it in a better way, and then we will make sure that you learn something during the lab. Okay. So any questions, or shall we stop here and meet again at 2:15 maybe? Okay, then it seems it's lunchtime. So Madhura, I'm kind of assuming it's this particular session is over now.
Yeah, all right. Yeah, thanks. See you later.
Yeah.